Hi, I'm your instructor, and I'm here to welcome you to yet another video about cells. As you all know, we've been discussing passive transport across the selectively permeable cell membrane, and today we're going to dive right into osmosis, the diffusion of water. Before we hop into osmosis and everything that it entails, I'd like to first do a quick review of what we've learned thus far about the different types of passive transport. So as we know, there are three different types, and they are, that's right, they are diffusion, osmosis, and facilitated diffusion. Now, I'd like you to take a second and jot down the first thing that comes to mind when you think of those three terms. And they're all very unique, so this should be interesting. So we know that with any type of passive transport across the selectively permeable cell membrane, there's no energy required. And again, the three types are osmosis, diffusion, and facilitated diffusion. What's very unique about facilitated diffusion is although it is passive transport and it does not require energy, it does require channel proteins, also called carrier proteins or transport proteins, to help materials get from one side of the the cell membrane to the other side of the cell membrane. And these transport proteins are also used in active transport. So that's something unique about facilitated diffusion. What's unique about osmosis is that it is the diffusion of water. Water is so unique, it gets a category of its own. And then regular diffusion would be the movement of particles from an area of high concentration to an area of low concentration. And we'll discuss what that means a little later on, but for now, let's go into osmosis. It's very important when we're discussing passive transport that we're 100% clear on exactly what the cell membrane is. This is a picture of the cell membrane. So now we're going to take a look at the cell membrane together. And we're just going to identify the key parts that would really help us zoom in on what osmosis exactly is. So we're going to ignore most of the parts of the cell membrane, even though they are important for memorization. But for osmosis, it's just important that we know where the hydrophobic tails are and the hydrophilic heads are that create the phospholipid bilayer, which is the cell membrane. So I'm going to pause for a second and allow you to identify where you believe the phospholipid bilayer is in this diagram. There's a closer look for you. So if you guess this area here, you're absolutely correct. That is the phospholipid bilayer, and that is what is used in osmosis. So like we mentioned previously, the cell membrane is selectively permeable, which means that it picks and chooses what it allows to go across it. Here is osmosis, which is the diffusion of water across a selectively permeable cell membrane. It does not require energy from the cell. So if we're going across the cell membrane, we'll think of this line as the selectively permeable membrane, and we'll think of one side as the outside of the cell membrane and the other side as the inside of the cell membrane. So take a look at this diagram and try to make some sense of it before I explain what exactly we're looking at. I'll give you about 5 seconds to do so. In this particular diagram, the side on the left would be water going into the cell membrane. So the side labeled hypertonic would be the side that the water is going into. It has more solute than it does water. Here's an important diagram that you should know in regards to osmosis. And it says the rule for osmosis: if the area outside the cell has more salt, then water will be sucked out of the cell. So, as we can see, there is a regular cell. If it has too much salt, the cells will swell and burst. If it does not have enough salt, then they will shrink and shrivel. Alright guys, so now we've reached the part of the osmosis lesson where it's going to require extensive note-taking and you really having to pay attention. So isotonic, hypotonic, and hypertonic. Basically, what you need to know from this, besides the definitions, would be that in an isotonic solution, we have a regular cell that we're used to seeing. In a hypotonic solution, the cell will continue to grow, swell, and eventually burst. And in a hypertonic solution, the cell will shrink and shrivel. So, we're about to get into some real world application of this, but that's just very, very important that you know those quick tips. All right, here we have a diagram of isotonic, hypotonic, and hypertonic. So again, isotonic is what we're used to seeing when we think of a cell. Looks like a donut, nothing special, it's just a typical cell that we're used to seeing. The top is a drawing, the bottom is a magnified example of what an isotonic solution would do to a cell. So next we're moving on to hypotonic. Really, really big. All of the solute molecules are coming in at a rapid pace. It's just getting bigger and bigger, it's swelling up. Hypo, like hippo, huge, humongous, enormous, it's huge, it's swelling, it's bursting. All right, next we have a hypertonic, which reminds me of a lot of my little 7th grade students. They're just full of energy, running, fizzing, jumping, leaping, and eventually they're going to fizzle out of energy. So let's just pretend that the salt particles leaving the hypertonic cell, let's just pretend it's energy in the 7th grader after lunch. They just seem to fizzle out and eventually they just dwindle away, and then we're left with our cells shriveling and shrinking in a hypertonic solution. So that's a real world example. So what have you learned thus far about isotonic, hypertonic, and hypotonic solutions? Based on what we've already discussed, isotonic we know is regular, it looks like a donut, and it's the perfect cell we're used to seeing. Hypotonic, big, enormous. And hypertonic, we're running out of energy, we're going to shrivel and shrink and eventually disappear. So I'd like you guys to, in your notes, jot down your example of a hypertonic solution and then share it with a neighbor if you have one, or if not, you can just share it with yourself. You see that little dot? Imagine that little dot is gray and it's just a regular cell, and it is about to be placed into a hypotonic solution. All right, so this is our regular cell, and this is our regular cell in a hypotonic solution. It's going to swell and grow and get enormous and eventually burst. All right, so here's one of my favorite diagrams of osmosis in action. We're looking at a carrot stick, and basically, I'll give you a second to take that in. Basically what happens is the carrot stick becomes limp when there's more salt particles on the outside of a cell wall than there are water molecules. And so the water that is already on the inside of the carrot will leave the carrot to join the salt particles on the outside of the carrot. I hope that's making sense. So basically, water's going to move to an area where there's less of it. It's always wanting to join its buddy. So water's going to move with water, which is osmosis, across the cell membrane, which in this case would be the carrot. And that's why the carrot becomes limp. So if water was moving in and out of the cell membrane or the carrot stick at the same time, it would be an isotonic solution, and the carrot would be very straight and firm and perfect, delicious to eat, and the cell would have reached equilibrium at that point. So it's time to put some real world application to what we've just discussed about osmosis, hypertonic, isotonic, and hypotonic solutions. So for this lab, you're going to need baking soda, vinegar, tap water, salt, Haribo gummy bears, clear cups, a measuring cup, and your camera for observations. Depending on how precise you would like your lab results to be, you may also need a ruler or a measuring beam. In this lab, I'd like you to consider the baking soda as a hypotonic solution, the water as an isotonic solution, the salt water as a hypertonic solution, and then use your critical thinking skills, and I'd like you to discuss with your partner or with yourself what you think the vinegar would be considered. What type of solution would the vinegar be? And write it down. Now, with each of the items that we use to do the lab, the vinegar, the tap water, the salt, and the baking soda, you must add 50 milliliters of water to each before you place a gummy bear inside of it. And also stir it so that it is a solution and not two different materials that are not even combined. When doing a lab, you always need your controls. So you need to set aside 4 to 5 gummy bears that have not been touched, altered, or dipped in any sort of liquid. You don't need them altered at all. You need them for comparison reasons. So when I began this experiment, I chose 3 cups per solution. So I had 3 cups for vinegar, 3 cups for baking soda, 3 cups for salt water, and 3 cups for regular tap water. And for those materials that were not already water, I added 50 milliliters of tap water to the solution. And then I stirred it together. So this is vinegar. I use red gummy bears for vinegar. And like I said, I just placed them in the solution. I left them overnight for about 12 hours total. Then I took them out. And now I'll show you a picture of what my results look like when I took them out overnight. This is what they all look like as they sat overnight. So I realized that you've had the opportunity to see what my results look like overnight, but I'd like to show you what they look like 2 days later, which I have before me. So, 1 second. So from my results, you can see that the gummy bears and the baking soda swelled. The gummy bears and the vinegar didn't really change size, but they were misshapen. The gummy bears in the water looked almost identical to the control, and the gummy bears in the salt water shriveled to almost nothing, and one of them almost disappeared. It almost completely dissolved. So that was an example of what the cell membrane, which in this case was the gummy bear, what it would do in various solutions. And as you recall, the water is an isotonic solution, the baking soda is a hypotonic solution, and the salt water is a hypertonic solution. So that just gives you an example that you can apply to, real world application of how cells react in various solutions. And like I said, the vinegar is what you believe it is. So that was my presentation on osmosis, specifically with regard to hypotonic, hypertonic, and isotonic solutions. I hope you enjoyed, and I look forward to seeing you for the next lesson. Bye.